So today is a re-recording of the lecture on the robust regression. We are focusing on the outliers in the training. In the previous time, people were trying to define where's the outliers, whether or not they are in the measurements, we would just normally call it outliers. However, if those outliers are the one that exist in the input features, we will call it leverage points. And the reason that we named it is because, in fact, those in the input features, we have some mechanism to find it. But for the one in the outliers, we could only recheck that with the training measurements. Or on the other words, we kind of use a technique that is related to the residual, or the computation of that y minus beta x. And let's say if this beta is the beta that we learned from, let's say, an algorithm, or maybe let's say in this case is the linear regression. If we have this one as being learned already, that means that this beta should somehow, absorb some abnormalities from both x and y. And somehow if you use it to recalculate y and it doesn't match y, or in the other words becomes like y minus y hat, and there's some mismatch between these two, it somehow could indicate there's some, like something that definitely went wrong from beta, and that beta came from a pair of data, and therefore we can somehow suppress those error. But usually when we use a residual, when we try to suppress the errors based on residual, usually it means we now don't care about where the outliers is, whether or not it is in the input features or in the measurements. We treat it the same way. And anyway, let's put this way. If we have a pair of data, let's say x, j, and yj, right? And if yj went wrong, and what you would do normally is that you remove both xj and yj. You wouldn't just remove yj and, left to xj be mapped with nothing, right? Or sometimes what people would do is that they probably change yj. That's another way to do it. But okay, in this lecture, we will talk about how shall we manage. If, let's say, we found out if xj or yj or both are incorrect, the only mechanisms that we would consider dealing with it is either remove or suppress both of them. We wouldn't just deal with only x or y. We would do both operations. We will remove both of them, or we will suppress both of them. That's it. Okay. And for today's lecture, we will focus on two types of techniques. The first type of techniques is called the outlier diagnostics. And these are the techniques where we will use to check and remove. Just check and remove for the outliers in training. We will check and remove the pair of outliers in training. Then you may use, the indication of where the outliers are, and then with that, you may, remove those training data and reapply the linear regression. Or maybe you may know where is the outliers and then maybe use the next method like the weighted least square to suppress those outliers. So the philosophy here is like, well, there are only two ways, right? As I mentioned before, to deal with the outliers. You either remove or suppress. And if you want to suppress outliers, that means you know exactly where the outliers are. And you kind of like, you only want to minimize the effect of those outliers instead of totally remove it. Because somehow, if you think about it, If these types of outliers exist in our training, that means that it reflects some kind of behaviors, and maybe it provides you additional information that could be useful for your algorithm to estimate for the model parameters. So that's the reason why we can remove, but sometimes we choose not to. And yeah, the other group of the method that we will talk about today is called the robust regression. And for these types of the techniques, we will talk about how shall we suppress. Yeah, we choose for this group we choose to suppress and re-estimate beta. And usually the re-estimation of beta is done with types of the technique that we call robust regression. And it's actually like a new technique that we will learn today. And again, we are talking about the outliers in the training. And finally, we have a page that summarizes each of these techniques. So as we mentioned before, that normally there are two places where we could look for outliers. Either it's in the measurements or in the input features. And the following are example where, like just a general example where if there are outliers in our training, it could cause problems in linear regression, for example. Like in this example, these red dots here are outliers, and perhaps if it's integrated into our data, the thing is, without these points, your regression will give you this linear regression mapping line, which align with the majority of the points except those trees. However, if you have these 3 points in your data set and you do the calculation of the regression, you may get another mapping line that's down there. And the reason that, these 3 points, although being the minority, it can severely change the mapping is because of the fact that the linear regression sort of relying on the least square error. And least square error, the square error, will very likely emphasize on those outliers. And the reason is because the residual due to these outliers is very high. That's the reason why. And also, the similar behavior could apply to those algorithms that has or maybe relies on these types of optimization where the norm of the residual, or maybe, okay, I'll just write it down. Okay, linear regression is just one of that. But, you may encounter with these types of formulation, right? It doesn't matter what f is, but if you use this residual norm, the L2 norm, the thing is, when there are high mismatch between your measurements, the majority of your measurements, and whatever predicted from your machine learning, the residual norm would tend to emphasize on those errors that are high or those residuals that are high, and it will cause the beta to behave in such way. And because of that, when the residual is high, and usually it's caused by these outliers, then you get the beta hat that is the result from this optimization to behave in a way like the purple line. Even though it doesn't match with the majority, but it will sort of being dragged down by these outliers. So that's the reason why in most cases, we will consider deleting these points or remove them. Or in some algorithm that we will learn today, we will just suppress them. And in the following example are, they're easy example where you can definitely guess where the outliers should be. And in this case, it's like the outliers definitely in the measurements, right? Because we have like a sort of increasing input features, and then it incorrectly mapped to some of the measurements in here. But this is like an easy case where you could guess that probably the outliers are in measurements. But sometimes you get something like this. Even though here we say that is the example where the outliers are in the input features. But the thing is, initially we may feel like, these input features definitely should be somewhere here, not here. But you could never tell. Thing is, it could be the incorrect mapping of the measurements as well. Like the measurements is mapped here, but not there. It's something like that. So, as I mentioned before, it's hard to tell where the outliers are, and sometimes it's not A, measurements, or B, the input features, but it's both, right? But the method that we use to identify the outliers sort of separate that, like in the following methods that we would learn today. The hat matrix, this will be the one where you somehow could use to find the outliers in the input features. And the rest will be used to find the outliers in the measurements. Or, it would be the one that identify, okay, I'll put it this way. It's identify outliers based on residual. And in fact, when you say it's based on residuals, it's hard to tell whether or not that outliers are in the input features or whether or not it is in the measurements. But for this one, it could only identify outliers in input features. And we will call these outliers again, just to recap, the outliers in input features as the leverage point. Okay, the one with the problems, we will specifically name it high leverage. Okay, it's like a point with high leverage value, but we'll see what high leverage means in the next slides. This is to recap what I just said. Before we move on to the techniques, let's recap a little bit about the linear regression that we've learned before. So in this system, let's assume that we have like a pair of measurements and input features, where M is the number of training data and N is the dimension of the input features, such as, if you use images as your input feature, then N shall be N of RGB image, right? Yeah, shall be 3 because there are 3 channels. Or if you are dealing with like a linear regression of some time series data, then N shall be the types of data that you use, like in our example of our homework is like the house price. Then N could be like the size of the house, the number of bathrooms, the areas of the house located, and altogether they will be used to identify the house price, which is our measurements, right? Okay. And the structure of your input features are as follow, where the number of rows shall be the number of training data, and the number of columns shall be the dimension of the input features. Okay. And in here, because we are considering the setting where we are using the linear regression, the way that we predict our results from the regression will be that we multiply input features with beta, that is like a linear weighted, that we estimate from the least square minimization. And this here is the formulation that we normally use with the linear regression, right? And here again, I just recap. Then, after we can estimate the beta or the weight in the linear regression, how can we calculate this with just one step calculation, that is to do pseudo inverse of x with y. And also in fact, if we do the calculation of y minus x beta ls, the one that we learned from this, we will get what we call residual, right? Because this is like the estimated measurements of our training data. And because it's a training data, then we know what y should be, what the measurement should be, and therefore we can find the residual, that is the mismatch between whatever beta ls that you get from training and the actual measurements that is from the training. Okay, and yeah, this is something that we will call residual error, and we use this quantity to identify the outliers in our training part of it. In fact, the first technique that we will learn will not deal with this residual yet, but we will deal with the pseudo inverse that is like a property that we use to estimate the beta ls. And we know that for this pseudo inverse to work, somehow x transpose x multiplied with x transpose x inverse, this is supposed to be close to the identity matrix, right? If this inverse work, and there are some properties with the nullity and all that, and with that knowledge, actually we use this knowledge to first identify the outliers in the input features. In fact, this page is just like we are trying to link how could you use this hat matrix. One way to use this hat matrix is that if we apply that beta ls that we've learned from previously with the x test, right? We can decompose beta ls into this pseudo inverse with y, that is the training in measurement. Okay, just notice that all of these group of matrices and vectors are in training, right? Except this one, that is the only input features at testing. And whatever this is, the final product is supposed to be something that is close to the measurements at testing. And thing is, if we were to consider only only the input features, whether or not it's in training and testing, we could group it as a matrix that is called the hat matrix. And in fact, if you consider this hat matrix being like a projection matrix, right? You can see that one of the function will be that you can actually use this projection matrix, the hat matrix, to map the impact between your measurements at testing versus your measurement at training. And that is one of the function. Let's say if your hat matrix doesn't, if you put the hat matrix this way, it's kind of telling you roughly that this hat matrix supposed to be close to the identity matrix. And somehow, if your measurements and your training data somewhat goes together well, and everything here is mapping well, this is supposed to be close to identity matrix. But it's not going to be, because of course the number of testing and number of trainings are going to be different. But anyway, this is like one of the functions that you could use for the hat matrix. And also, yes, you can use this knowledge to find then if there are some mismatching. So could you identify some outliers, like where is the mismatch between the testing and training? Of course, you can use that knowledge because that this is supposed to be close to identity matrix, and perhaps you could calculate a threshold by summing over all the elements in the diagonals, or maybe the closest to the diagonals, because I know that hat matrix will not be a square matrix because m and m prime, and in here m prime is the number of testing. Yep. This number of testing is definitely much smaller than the training. And of course, you wouldn't get like a square matrix for a hat matrix, but you can somehow know that if the mapping is correct, then somehow this HJJ is supposed to be close to 1. And then if you sum over it, it's supposed to be something that is, supposed to be about less than or equal to the number of the feature dimensions. And with that, we provide the following information for you to consider. Let's say the first reason that I use mean between m prime and m here is because, we may not know, at the deployment phase, whether or not you have higher m or m prime. But anyway, we want to calculate with the tightest bound, and that's the reason why we try to find the lowest possible number of m to be the denominators, and in most cases m prime will be smaller than m. And for the denominator, we said it should be n, here, this number here. The reason is because if you think about hat matrix being close to the identity matrix, which I approximated here, the sum of the trace is supposed to be n. And yes, that become like the boundary that we set up here, that if there's any HJJ having value higher than H bar, then that means that HJJ is definitely having some kind of problems. But thing is, with this analysis, we are talking about the mapping between between Y testing and Y that is from training. But actually, there are problems with this mapping in general, because not only there are some possible mismatch between them, but also there's some possible mismatch between X test and X train. That's the reason why in our first outlier diagnostic, we will consider where X test is just the same as X train, or on the other words, we will only consider finding just the mismatch among X in the training. We wouldn't think about the one in testing and training. And the reason is that it's for this first case where we are focusing on finding the outliers in the training, it's just simpler that way and straightforward. And for that reason, as we know that, okay, if we consider both training and testing, we use this formula. But if we only consider the training, then that means that we can minimize our formulation to be n over m. And this 2 number here is like a scaling value where you could adjust it to be 2, 3, or 4, depending on how loosely you want to consider the hat matrix elements to be the outliers. Let's say if this scaling is high, right? If you use the multiplier to be 2, 3, 4, then that means you allow the HJJ or the diagonal to be off from the identity value, to be far from being identity. But if you define this scaling to be, let's say, 1, then that means HJJ definitely has to be like closest to the identity matrix possible, because the 2 over m, not m prime here because we only consider the training. This n over m here, is like it's tightly bounded to the possible value of this hat matrix to be. Like it has to be strictly identity, therefore the upper boundary shall be n, right? And if anything that's beyond that, that means you can consider that HJJ being corresponding to the J data points that are outliers. But if you increase this scale, that means that there are chances where that HJJ may not fall into these categories. And of course, we have name for it. For any J points that have high, that leads to the high hat matrix diagonal coefficients, we will call that point, the point that give high we call it high leverage. Okay, and that's it. In fact, in this example, you will see that in fact you can normalize this. You can set different value for this, and in this plot, actually this should be M. If we consistent with the definition, right? In here I kind of copied the example from the textbooks, and here is supposed to be just M. And so yes, in fact, if you have input features, you can automatically, right, find your hat matrix, and you can automatically calculate the trace and check if it's beyond, or maybe find if any of these diagonal coefficients went beyond the value it is supposed to be. And so hat matrix become an easy techniques that you could use to find whether or not your input features somehow behave in a way that it's supposed to be. And in fact, you can use these properties in multiple settings, because just think about the fact that if your input features, the pseudo inverse is possible, then that means that your input features somehow start to behave orthogonally. And with that, the orthogonality of the input features are in fact quite important in many applications, including, like in here it's just regression, but also including classifications, detections. And that's because your input features should allow the unique mapping, right, to your measurements. And with that, you could mostly get the correct mapping results. So yes, that's one properties that you could use in many algorithms. But in our lecture, you'll see that in fact, if you can identify, that these points are outliers, if you have the knowledge of the position of these points, then you could use this location with the other algorithms, like the one that I mentioned before, like the weighted least square algorithm, that you will use those location and you will say, okay, I want to suppress the data points. I want to suppress the effect of these data points in this location, and I will weight it down. Then that becomes the weighted least square algorithm. So simple as that. Okay, let's continue with the other two techniques that we can use to remove the outliers. So the other two techniques will based on what we call the residual analysis. Okay, let's start off with our initial idea. Just like previously, the hat matrix, whether or not this is X or X test, is supposed to be close to the identity matrix. And that's one of our knowledge. And because it's supposed to be close to the identity matrix, you can use that to analyze the residual. And with that, let's say if we remove a data pair from Y and X, right, it will impact the calculation of hat matrix, and your measurements Y will be shorter. And with that, if you remove those points that are deemed to be outliers, then that means that you should get the estimated measurements that is close to your target measurements, and that should lead to the lower residual. And this become like a core idea where you specifically remove data pair, and you use that removed set of the training to calculate the residual, and you checked whether or not this residual is low enough. So that's like becomes the core idea of the other two techniques. And the first one we call residual analysis. Sorry, the name is just the same because this one will directly, employ the previous idea to this data removal techniques. And basically, it's very similar to what I just said previously. The only difference is the fact that it actually, not just calculating residual, but the normalized residual with some of the residual standard error. So the techniques go as follow. Okay, as I mentioned, what if we remove, right? If we think about, we have the measurement y that is a vector here, and we have the x. Okay, I'll just put it here, right? That is input features, and for x is m times n, for y is n times 1, m times 1. If we remove, let's say, the pair j, right? Then for x, we would do the same, right? And it becomes a new matrix. After we removed, we call it x minus j. And now it will be m minus 1 times n, right? It's just shorter, the same similar matrix, but without this row. Likewise for y, is like a similar vector but without that row, so it becomes y minus j. And in here I actually used minus j to denote the vector or matrix whose row j has been removed. And once we have this, you can think about the fact that, in order to calculate the hat matrix is defined by xj transpose x multiplied with xj transpose x inverse, right? Therefore, this is n times n. This is also n times n. Therefore, whether or not it doesn't matter how many rows you removed. It wouldn't impact the dimension of each matrix or your hat matrix. And sorry, maybe I done something wrong. Sorry, okay, the formula wasn't like that. Okay, I'll put this way. Let x be okay, anyway, I'll just check previously. Sorry. Hat matrix is x and x transpose x inverse and x transpose. Okay, sorry. So this will be m times n, and this shall be n times n, and this shall be n times m. And so if you remove x, right? If you remove x, of course, it will impact what your measurements y could be, and also the dimension. But the thing is, you can still calculate this residual. But I think you can also tweak it a little bit, like in the following. In here, you can actually still calculate beta, and you get the same dimension for beta. I'm sorry, maybe we wouldn't go with this. Okay, sorry. I shouldn't tie it to the hat matrix. Okay, let's put this way. After we remove that j rows, right, we have xj, yj. How shall we calculate beta? Beta is x transpose x inverse x, right, and y. Thing is, transpose, right? This is n times m, and this is m times 1. This is n times n. Thing is, regardless of whether or not you remove that J rows, you still get beta with the dimension of n times 1 anyway, right? Sorry that I typed it hat before. So this will be, you could just keep this. In fact, in our example, we keep it. In our example algorithm, we keep it. Xj minus j transpose y minus j transpose, so not transpose, just y minus j. So this become m minus 1 times n. This become n times m minus 1. This is n times n. Yep. With that, it doesn't matter if you remove the j row, you could still be able to calculate beta with the same dimension anyway. But of course, if you remove the j row, your beta value will be different. And for that, we actually have a notation for the beta that we calculate without such j row as beta j minus, like that. And of course, that beta j will still have the same dimension as the normal beta that we can calculate with the full rows, with the matrix with the full rows. So we know that these two should be approximately similar, right? But the thing is, if we imagine, if we are able to remove that j rows that cause problems, right? So that means that if you calculate the residual being, like right now, I wouldn't try to tie it with the hat matrix. If we calculate residual being y minus beta x, and this is x minus j. Sorry, I swapped the location. Yep. Yep. Okay. If we calculate this somehow, okay, I'll do it this way. If we calculate this and it just turned out that we have a much lower residual, that could mean that the j rows that we just removed are the one with problems. And that is like the main mechanism that we would use for this residual analysis. And it goes as follows. So yes, firstly, you calculate the beta ls, just like here. You got it here, right? And beta ls has the same dimension as beta x. Sorry, as a generic beta. In this example, in fact, you could one way, you could keep x. If you believe the outliers are in the measurements, you could keep x. In this example, they actually keep x. Yeah, in here you can also keep x. If you keep x, right? If you keep x, it's possible as well, because it doesn't matter. You can still got the where is it? You still got the m times n, and this is m times n. If you could remove that one pair and the rest of it still align with the majority of your measurements, then that means that in fact that pairs that you use to calculate beta j minus is causing the problem. And that's actually the kind of idea. If you can remove, okay, the idea here is if you can remove that j pairs that's being used in calculating beta j minus, that means, and I mean by can remove, I mean you get a low residual. Or if, on the other words, if you removed it and your residual become lows, then that means that j data point is the problem. Yeah. But in this case, in fact, we checked that residual not by the direct checking. We actually have to do some scaling, and the reason for scaling is because we want to make sure that this d minus j, or the residual, once we remove the data points at j location, are just by accident becomes lower. And it's like once you have this the normalized term is kind of ensure that this value here could be somewhat standardized into a value. In this case, let's say if you set up the value of this residual to number 3, somehow it could be reliable because you're now normalizing the norm of your residual. And once the norm is normalized, it's usually being distributed within like a standard deviation. So that number 3 shall be like in correlation like 3 times of standard deviation. Therefore, it's kind of reliable. It's just to make your thresholding becomes more reliable. Yeah. And residual analysis is straightforward in the sense that you consider removing data pair, and if data pair help you with the residual, then that means that data pair is definitely the problem because you removed it, it gets better. But the problem with these types of algorithm is the fact that if you have to keep consistently remove that J pair, and if you have like 1,000 or maybe 10,000 of your training data, then that means you have to calculate this and this for, I don't know, 1,000, 10,000, I don't know. If it's like 1,000, right, that means you do it twice, maybe like square of that, which is not great. You probably want something more efficient, and that leads to the Cook distance algorithm. In fact, this algorithm has the same idea, and as you can see, it's actually changed from using the residual, like just the normal residual, to like a square of the residual. But that is done for a reason. It's because it can actually allow you to reshape the formulation such that, and in here I actually provided in appendix page 33, you can click and see where that formulation came from. And with that formulation, that you get from the Cook distance, and this time we call it Cook distance because is this guy who think about reformulating the norm into square of norm. If I remember correctly, it's the name of a person, but I'm not sure. Maybe it's a distance-wise base name. But anyway, with this reformulation, it enable you to be able to identify the J data point pair that cause problem by, instead of removing one J data point and recalculate, you could just find that J data points directly by reshaping this formulation into some residual times the hat matrix. And as you know before, hat matrix could be calculated regardless. Like it could be calculated if you have input features. You don't need to even have like measurements. You can just calculate directly. But in this formulation, simply means that you don't need to keep removing that J data point in order to check all of that. You could just use this hat matrix with some residual calculation. Then you get the identifier, DJ matrix. Sorry, DJ here is a coefficient, but altogether it's a matrix. Not matrix, it's a vector. And you can use this DJ vector to find where is the outliers. And this is actually your homework. And the reason that I put it as homework because I want you to see, that you can actually find the Cook distance quite efficiently. And then you can identify the outliers as well. But the outliers identified by the Cook distance will be somewhat different from the one that you get from hat matrix because you have this residual term multiply with it. Therefore, the decision will be different. Anyway, another thing that you should keep in mind is that this n here is the number of input features. Yeah, that's it. I think because some students might incorrectly input different value. But anyway, this is your homework. I wouldn't say more. I will leave it to you to check and analyze it. And yeah, let's go to other topics. Oh, yeah, before we go. In fact, once you use this formulation number 5 to find the cook distance for all of your data points, you can use the same technique as the hat matrix where you set up a threshold and cut those points off. The points that go beyond your threshold. It's definitely outliers. But this time, the difference will be that it's not just outliers in the input features now, because you use the residual is also the points that being identified by, the factor of being outliers based on the residual. That means it could be the outliers in the measurements. But as I mentioned before, we could never know whether or not this is like a true outliers or not unless you actually go into your data to check that, to check how abnormal that was. And yeah, that's actually homework to analyze whether or not you get the same result from cook distance versus hat matrix. But as I mentioned before, it's not going to be the same. But it's your task to tell me what's the difference between them, to analyze differences between that two, right? And yes, let's pause a little bit before going to the next topic.